Hello all. In this session, we'll discuss about the logical instructions of 8051 microcontroller. So as you know, the AND, OR, XOR, rotate and the swap, these are the various operations done in the logical set of instructions. And the list gives you the mnemonics associated with the logical instructions. AND logic, OR logic, XOR logic, clear, complement, rotate left with carry, rotate right with carry, and swap. So first let us discuss the ANL instruction in detail. So ANL comma destination byte comma source byte. So this instruction performs the logical AND operation on the source and destination operands and stores the result in the destination variable. So as you can see, always the Intel follows the opcode destination comma source. So here the content of the source will be ANDed with the contents of the destination and the result will be again stored in the destination variable. So let's understand with an example. Move A comma R5. So for example, before execution, assume that accumulator has some 22H and R5 has some 32H, and I'm sorry, it is not move, it is AND ANL A comma R5. So when we AND the content of the R5 register with the accumulator register, so A is 2, so 0010 0010 and 32 is 0011 0010, and we know that for a AND gate, when two inputs are high, when both the inputs are high, the output is high, otherwise output is 0. So first 0 0 is 0, when two inputs are ones, output is 1 0, and again when two inputs are different, then output is 0. When two inputs are same, output is 1 0 0. So you can find that whenever both the inputs are high, the output is high. So the result is 22, and after the execution, the accumulator has 22H. So this slide gives you the various forms of the ANL instruction and logic instruction. So ANL, first one ANL A comma hash data. So the content of accumulator register is ANDed with the immediate data, immediate 8-bit data, and the result is saved in the accumulator register. And here in the second, the content of accumulator register is ANDed with the contents of the register Rn, which may be any register from R0 to R7 of the register bank 0, 1, 2 or 3, and the result is saved in the accumulator register. Next is AND logic A comma direct. So here AND logic A comma direct, the content of the accumulator is ANDed with the content of the internal RAM location given by direct, and the result is stored in the accumulator register. And next ANL A comma @RI. The content of accumulator register is ANDed with the data pointed by the RI. So here Ri may be R0 register or R1 register, any one of the R0 or R1 register. So the content of accumulator is ANDed with the data byte pointed by the R0 register, and result is stored in the accumulator register. Next, direct comma A. The content of the internal RAM location given by direct is ANDed with the content of the accumulator register, and result is saved in a internal RAM location. Next, direct comma hash data, ANL direct comma hash data. So the content of the internal RAM location given by direct is ANDed with the data, immediate 8-bit data, and the result is stored in the internal RAM location whose address is direct. So these are the various forms of the AND logic instruction. Next, OR logic, destination byte comma source byte. So this instruction performs the logical OR operation on the source and destination operands and stores the result in the destination variable. So it basically performs the OR operation on the source and destination, and the result is saved again in the destination column, and no flags are affected. So for example, ORL A comma direct. So let's take an example for this. ORL A comma, let the memory location be some 23H. So before execution, A has some 23H, and the content of 23. Let's not get confused with the same 23. So let A has some 10H, and the content of 23 be some 11H. So now ORL A comma 23. So the contents of accumulator, 0001 0000. This is the content of the accumulator, ORed with the content of the internal RAM location given by the direct. So which is here 23. So the content of the 23 memory location is 1 1. So for a OR gate, any one of the input is 1, the output is 1. If any one of the input is 1, the output is 1 for the OR gate. So the result is 1 1, and which is saved in the accumulator register. So this is how the OR operation is done. Now this slide gives you the various forms of the OR operation. OR A comma hash data. So the contents of accumulator are ORed with the immediate 8-bit data, and the result is saved in the accumulator register. And here in the second, the content of accumulator are ORed with the registers, any register from R0 to R7, and the result is saved in the accumulator register. A comma direct. So the content of accumulator register is ORed with the content of the internal RAM location whose address is given by direct, and the result is saved in the accumulator register. And next, A comma at the rate ORL A comma at the rate RI. The content of accumulator register is ORed with the data pointed by the RI register, and the result is saved in the accumulator register. So this Ri may be R0 or R1. Next, the content of the internal RAM location whose address is given in the instruction is odd with the content of accumulator register, and the result is saved in the internal RAM location whose address is given in the instruction. Next, ORL direct comma hash data. The content of the internal RAM location is odd with the 8-bit immediate data present in the instruction, and the result is saved in the internal RAM location whose address is given by direct. Next, XRL. So XRL destination byte comma source byte. So this is a logical XOR operation, exclusive OR operation. So this instruction performs the logical XOR operation on the source and the destination operands, and the result is stored in the destination variable. No flags are affected. So let's take an example to study this. So XRL A comma R3. So again assume some values. So before execution, A has some 22 and R3 has some 33. So A 0010 0010 and R3 0011 0011. So XOR operation, it is a XOR operation is also known as modulo 2 operation. So when both the inputs are dissimilar, when they are not same, the output is 1. When the inputs are same, output is 0. Output is 0 when the inputs are same, and output is 1 when the inputs are different. So after execution, the accumulator A will have 1 1. So this is about the XOR operation between the source operand and the destination operand. So next slide gives you the various forms of the XRL operation. So we have XRL A comma hash data. So the description, the content of accumulator A is XORed with the 8-bit immediate data, and the result is saved in the accumulator register. Next, XRL A comma Rn. The content of A is XORed with the content of register, and the result is saved in accumulator A. Next, XRL A comma direct. The content of A XORed with the data present in the internal RAM location. This direct indicates the data is present in a internal RAM location. So the data byte is XORed with the accumulator A, and the result is saved in A register. Next, XORL A comma @Ri. So the content of accumulator is XORed with the data pointed by the Ri register. So here the data is present in the memory location. The memory location address is present in the register, which may be R0 or R1. So here we say it like the data pointed by the R0 register is XORed with the content of accumulator register, and the result is saved in the A register. Next, direct comma A, XOR direct comma A. So the content of the memory location, the content of the internal RAM memory location is XORed with the accumulator register, and result is saved in the internal RAM location. XRL direct comma hash data. So again, direct always indicates the memory location. So the content of the memory location is XORed with the immediate data, 8-bit immediate data, and the result is saved in the memory location, internal RAM location, which is specified in the instruction. So next is here clear A and complement A. So first going with the clear A. So this instruction clears the accumulator. All the bits are set to 0. No flags are affected. For example, if I write CLR A and if the accumulator has some 33H, that too before execution it has 33H. So after execution all the bits of accumulator are made 0. So the output is 00H. Next, complement A. So this instruction logically complements each bit of the accumulator once complement and no flags are affected. So let's see CPL A. For example, before execution A has, for example, 0, 1, 0, 1, 0, 1, 0, 1, nothing but 55H. So before execution A has 55H. So complement accumulator. So complementing accumulator means complementing each bit of the accumulator. So after execution, so the 0 has to become 1, has to become 0, 0 has to become 1, the complement of it. Yeah. So 1 0 1 0 1 0 1 0. So nothing but here AAH. So after execution, yeah, accumulator will have AAH. So this is the part 1 of the logical instruction group. In the second part we'll go with the rotate and the swap instructions. Thank you.